back. We're doing backprop today. This is attempt 3 of recording, and yeah, let's just get into it. Um, let's see. I want I want to swap me. Yeah, I'm in the corner now. Will, when you see this, let me know what you think. Do we want to draw on dark text, or do we want to draw on a white background with dark text? Part of me thinks that I might go with dark back. Let's give it a try. You know what I mean? You should always give it a shot. You know, I remember there was dark mode versus light mode, and you said light mode because it kept you awake. But I don't know. I think like 3 Blue 1 Brown. I think Khan Academy. You know what I mean? Like, ah, and what's the name of the guy? The chemistry tutor, the organic chemist or something. Mm-hmm. Okay, let's see. So let's do a normal neural network. Let's do NN. Okay. Don't ask me to spell too many things because I'll embarrass myself. I'm really just gonna have to try to recall this. At the end of the day, we want the partial derivative of loss with respect to, this is where we're already wrong, is we want it with respect to W, but it's like we want it with respect to all of the W's, and inevitably how do I say, in our neural network, what we'll have is, what are we gonna call our output? Not Z. We're gonna say Y equals sigmoid of, let's just do one layer. Yeah, because that's how we should help ourselves is, what's it called? Let's not complicate it. Let's say Z looks like that, and then Y equals sigmoid of WZ plus B. And now we have a 2-layer neural network, I'm pretty sure. Oh, you can't see that. Well, now I'm way too invisible. Okay. So now we have a 2-layer neural network, sure. But that's not particularly useful to me yet, being frank. Oh yeah, I made it so you guys can see that. See me selecting stuff now. Hmm. But basically is, well, that's not the same W. You know what I mean? That's W1 and that's W2. But what we want is our loss with respect to W for all of the W's. And it's almost like I'd want to have, this is very strange, because we kind of want a gradient. The gradient we want is a matrix. You know what I mean? It's like we want, does it even matter? Like, yes, it's a matrix, but I don't even know if we're going to be intimidated by that. Because loss with respect to the gradient of loss with respect to W is going to be something like the gradient of loss with respect to um W01 or 10 or whatever, and then it's going to like expand. You know what I mean? That's what that would look like. I'm fairly sure. And like, who cares? Because that's just what it's going to look like. And it's so that you could map that over the actual matrix and like, take your small gradient step in the direction of steepest descent. Like whatever. Um, so you want all the partial derivatives for all of the parameters that are captured by the weights. That's our goal. How are we going to get there? The chain rule, and even further, both the chain rule and the function of the neural network. So how do I want to do this? Let's draw, it's not the smallest case, but let's draw logistic regression. I think that is the most trivial matrix oriented gradient descent solution I know. So what I want is y, which will be bounded by, why won't you let me draw? I want y, which exists from 0 to 1, to be sigmoid of wx plus b. Is it as simple as that? Do I want bias? I feel like I should. I think there's a world in which I don't. Like, for example, with large language models, they actually don't do a bias. There's actually a reason for that. So let's say, let's do a small dash. Let's say, that is so useless. That's so tiny. And say question mark. What? Hey man, let me write. No in LLM. What? Why is there no bias? I don't know. And what does this look like? Is can I represent this as a story? We have X. Let me see if I can do a better blue as well. I wonder if this is hard for you to see or not. That's definitely a better blue. I don't know if it's a sufficient blue. I also don't like where I'm being placed in these videos. I prefer myself in the upper right, I think. No, guys. Oh, yeah, this is what I'm supposed to do. And there's no way for me to, I can't just do this. You can't even see that. I can't just do this on my iPad because the second I move, it doesn't work. But I don't know. Let's try it. Let's see if I can give myself an imaginary line and I don't mess with it. Um, so let's move these and I'll say that, what are we looking for? Was I going to draw it? Oh no, let's say like, let's take X. Because let's say X is a vector and X captures some features. We're just going to do two dimensionals. Or yeah, X is a two-dimensional vector. Whether or not you write these with brackets or parentheses, I don't think I care right now. Oh, vectors are drawn with, this is bad. But it's not even a vector, like we're not in calc. Whatever. Let's do a vector and then let's give it coordinates. Let's do 2, 5. Okay. And that's X, and then we also have W, and W's a matrix. Yeah, see, I don't like it. I take it back. I do care. I want brackets. Because it's a 1x2 matrix. Everything's a matrix. So I want a, let's see, 7, 4, 8, 9. And that's W, and then B equals, oh, and completely ignore, I guess we can't really. It'll come to us at some point. But are we doing row-wise linear algebra or are we doing column-wise? I think the fact that I've written Wx has actually made the decision for me. So this means a 2x2 must intersect a 2x1 to produce a 2x1, which means that X is 2 rows in 1 column. So the right is column-wise and the left is row-wise. So we actually have, per our initial equation, X is this and bias is that, because we're working with columns. And there's actually, and I've already messed this up, there's actually like a debate. I think there's like a confusing notation in like the quick tangent. There's confusing notation in the machine learning research space, I guess. I don't know. I don't read research papers. I'm just kidding. What's it called? Because you can do this operation row-wise or column-wise, but also in contrast to, and this is row-wise, and I think I prefer row-wise. And let's see, AX. But linear algebra prefers column-wise. Like traditional linear algebra prefers column-wise. But if you imagine a neural network that you read left to right, is you do W, or you do XW plus B, um, W plus B. You know what I mean? And you sort of chain out. When you're reading it as a this would just be a one vector. You got to give at least two. When you're writing it like this and you have like W, like this is W, this is X, this is WX. And even worse, it's actually XW. And what's your source of confusion? You have to choose one. I don't know, you wrote this vertically, so maybe you want it to be a column, but also you're going to read it left to right. And this is reading it left to right. So do you want it to be a column or do you want it to be a row? You have to decide. And I don't know what the standard is for literature. I think it might be the classic linear algebra, because that's probably more traditional or something. Okay, tangent over. Okay. Yeah, I think I'm just gonna happily take like longer than I need to and like never get to doing backprop for an actual LLM. Okay. Um, so this is XWB, and if I were to draw this, it would be 2, 5, 7, 4, 8, 9, plus 1, 2. But that's still not what I'm looking for. This is what I'm looking for. I want this, and then I want this. Nope. What connection am I missing? Okay. So this is X. This is, oh, and then we're missing B. So we're going to do this. And then this is W, and then this is B, and then this is Y. And what we're missing is an activation. So technically, we're actually going to wrap all of this in sigma. Let's see. And I'm not sure I've done anything productive by doing that. Oh, you can't see it. Um, hmm. What do we think? Let's just take this. You know what I mean? We're looking to do gradient descent on both our weights and our basis, bias, whatever. Um, so what's sigmoid defined as? That's our first evil. Is, oh boy, sigma of x equals, I'm such a disappointment. Let's see. We want it to look like this. That's not even good. That's still not. What are we doing, guys? Closer to that, and this is 1. This is 0. This is 0.5. So how would we do that? We want really negative values to give us, let's see. It can't possibly be this. I'm mixing up sigmoid with softmax. This is not sigmoid. I'm gonna look it up on my iPad. Cool, I can do that and it doesn't break the stream. Let's see. Let's see. Sigmoid. Oh, there it goes. Ah, 1 over. Oh, it left and then came back. That's the best it's ever done. What's it called? Dude, this app for like streaming my iPad to my computer, horrible. Okay, 1 over 1 plus e to the minus x. Does it work? Does it form the shape that I'm expecting? Um, Big numbers. If this is a really big number, this turns to 0, we get 1 over 1, okay? If this is a really negative number, um, and if it's 0, this is half, yeah. If it's a really negative number, then this is really big, and then 1 over infinity, 0. Perfect. So this is sigmoid, and then, um, guys, this is rough. But this is what, like, recall is supposed to be. So, how would I write this? Is if, nope, nope, come on. Sorry, issues. Is if I want to do, I want to write sigmoid with respect to x, and its derivative is actually something very clean. So I'll probably exit my iPad again. I'll first try to recall it, but I don't know what it is. Is it something like sigma prime of x equals, see, okay, let me say off the top of my head, is I want to say it's something like 1 over 1 minus sigma to the x. That's like what I want to say off the top of my head. I don't think it's this. Can I truly embarrass myself and show that I don't know how to do single variable calculus on YouTube? This is just literally straight up calculus. Let's see. With respect to x, that is 1 plus e to the minus x to the negative 1, as far as I'm concerned, which is negative 1 to the 1. Interesting. Let me not cheat. To the 1 plus e to the minus x. Times to the negative 2 times, what's this respect to x? Times negative 1 to the e to the negative x. So what are we looking at? These cancel out. We can get e to the negative x. Why am I doing this? Plus 1 over 1 minus e to the negative x squared, which is 1 over e to the x. Oh my gosh. 1 minus e to the x squared. Let's see. It's supposed to be, it goes very cleanly into its own self. Ooh, I wonder how I messed this up. This plus became a minus. Plus. No, it was a plus the whole time. Okay. So actually, so we already have sigmoid squared. Hmm. Yeah. All right. I'm cheating. I give up. Let's see. Derivative of sigmoid. So I just failed that interview. That alleged interview. Let's see. I can save this to my camera roll. Yeah. Save images. Save photos. So, what does the math look like? But like, okay, I'm being a little bit dangerous and like irresponsible of like my time, but also if I can't do this, I can't do. You know what I mean? Like I don't I would prefer to do top down. I care about doing top down. But this is an important exercise because how am I going to be able to to show to myself the math that produces the gradient? I don't want to say, oh, we just take the gradient. You know what I mean? If there's something different that ends up going on, I need to attempt this to formalize my question. Let me just keep lying to myself that I think this is worth it. Okay, so we have our normal sigmoid with respect to x. Okay, we have the squared one. See, I don't like when they just magically do stuff. Okay, so this is times. Okay, that's fine. Yeah, that's actually fine. Whatever. And then it's e to the negative x times negative 1. Okay, cool. And it's, yeah, it's the fancy algebra that they're going to do. So here, they exploded the exponent. Sure, because I would totally do that. And then multiplied it by e. Wait. And then where did we get 1 minus? See, how am I supposed to know that this is 1 minus sigma already? See this part? That being equal to 1 minus sigma of x. Dude, I don't even, like, that's algebra that I'm not sure I could do. 1 minus this is e to the minus x is 1 plus e to the minus x over 1 plus e to the minus x. Oh. What is it? It's minus. So it's minus 1. Okay. But then it would be a plus. Minus 1. Wait. Minus 1 over 1 plus e to the x. Am I not finishing something? Plus minus x. This is it. This is it minus. This is 1. 1 minus 1 over 1 plus e to the minus x. E to the minus x. Sorry that this is like an absolute mess for anyone trying to read. Because, yeah, I'm doing this for myself now. I'm like, what? Like, okay. It's embarrassing. You know what I mean? Like, I am showing myself, like, fumbling around doing basic calc. Um, but that's like a different. I'm going to do this. I'm happy to do this. But it is weird. You know what I mean? This is different than like school. This is me like trying to use calculus. And when you're like someone like trying to use something, it's like expected that you'll fail. And like, that's completely okay. It's different than like, oh, I'm bad at calculus. I'm gonna fail my class. You know what I mean? It's like, oh, well, if I don't get this, well, if I just keep going, I'll get this eventually, and that's completely fine. There is no like, I don't know. It's a different type of relationship. Um, I'm so lost. Minus 1. It would be positive. This is fine. Why is this negative? Once again, 1 minus this. It's not this minus 1, right? Disgusting. Is it from this? Is it that negative sign? Wait a minute. we have this, and this didn't move. And we're going to take this, and we're just going to multiply it. That becomes the 1. Okay. And now we have this, and we're going to multiply it by this. This is our literal sigmoid function. Dude, again, basic calculus. What am I missing? Do we go all the way back to the algebra? Oy vey. This is barely productive. This is truly, deeply, barely productive. This is me brushing up on math that I'm clearly bad at. Okay, let's give it another shot. Let's let's do it formally. Sigmoid of x equals 1 over 1 plus e to the minus x. Sigmoid prime of x equals. How would I do this? Let me just try it and ignore the math. I would write this equivalently as 1 plus e to the minus x, because I don't know how to do the, what's it called, rule. The division rule for calculus, I only use the power rule. So we're going to have -1, and then I'll refer to the cheat sheet because I'm going to get stuck because what's it called? This way of doing math is not fond of everything, per se. And that is going to be times -1 times e to the minus x. Okay. And this is equivalent to, I would already cancel these, the -1s. But maybe I'm not supposed to. Let's keep them. Doesn't make sense to me yet. So do I want this whole thing squared? And then eventually I'll expand it according to the other thing. -1. Okay. This is the -1 that's missing. I think this is the -1 that would fix my things, fix my issues. But I don't see a -1 hanging around here. So let's see. So now I explode it, and I have 1 over 1 minus e to the -x times 1 over 1 minus e to the -x times -1 e to the -x, which is equivalent to, oh, no, don't forget the -1. Okay, which is equivalent to -1, 1 minus e to the -x times negative e to the x okay, and how would I say, 1, just pull out this identity out of my ass, because of course, is equivalent to 1 plus e to the -x over 1 plus e to the -x. Nope. Minus 1 over 1 plus e to the -x. Which equals, if I'm not mistaken, okay, so this is the same thing as 1 minus sigmoid of x. So this is negative 1 over sigmoid of x. I mean, what's it called? This is sigmoid minus 1 or something. You know what I mean? Sigmoid plus 1? No, sigmoid minus 1. Um, but I have two negatives, so I would cancel them, and then I would have sigmoid of x times 1 minus sigmoid of x. I'm so confused. Dude, what voodoo am I missing? I got there, but it's that -1. What? Did I skip something? Guys, the internet would not lie to me. What? What the heck? Dude, there's no way that's like a top Google result and like the math is incorrect. Um, I don't think I have the patience. We're gonna take this as what it is and we're gonna accept it. Dude, what did I do differently? Someone in the comments, if you follow that math, I got the same answer, yet I have a floating -1 that I came up with or whatever. And they don't have this floating -1. And then importantly, they go from here to here, but I don't see how you get from here to here. I don't think that identity holds. I am very open to being wrong. This is weird that I just walked it through. Maybe I'm tired. Maybe it's the end of the day. I don't know what's going on, guys. Okay. So we got the the derivative of sigmoid with respect to x. Okay. And so we're here. All right. And we want y. We want the partial derivative of y with respect to w. Okay. And we're going to have to chain rule for that, which means we first need the partial derivative of y with respect to sigmoid times the partial derivative. Oh yeah, don't calculus wizards. I know a pure math student. I should probably ask them about this. I know two pure math students. I should ask them about this. Because I remember when I took calc for the first time, there's like weird things of like what this object is, like the partial y or partial anything, and like what you can and can't do. I still don't know what they are. They're just symbols. Like I really don't know what they are. I have no notion of like I have the notion of the object of a matrix. I have no notion of the object of why it's partial y over partial w. Because like you can have like how do I say? You can have x equals y, and you would write it as dx dy. And then you would say dy over dx equals 1, or dx over dy equals 1. And like you can divide them, but like you can't divide them. What's going on here? Like this transition of like, oh, you just derive both sides, or you just take the derivative of both sides. I'm foozy woozy on that. I don't know how that one works, guys. Don't know how that's allowed. But so it's technically this is what the chain rule is so we want what's on the inside of this is the oh no, maybe that's part of why it's weird. Is you have to do it because of the plus, it's like the partial derivative of with respect to w. Wait, yeah, we don't even want the derivatives with respect to x. So x doesn't even really exist. Um, wait. This is what I'm spacing out, man. I should be able to do this. Chain rule is it's the derivative of this times the derivative of the inside of this with respect to w. Oh, which means there's no derivative for b. The derivative of this with respect to w. It can't be that simple. Is it that simple? Is this just a two-step one? Is it just times the, you know what I mean? Would we call it a day here? This is the derivative of x of y with respect to w for the same x. Oh. But you have to. But w. But yeah. But b. B is something that we want. How would I do this? I would just do the partial derivative of y with respect to b. Oops. Times 1. Is this supposed to be multiplied by x? I think so. X is a constant in this case. And we want the partial derivative of sigmoid with respect to w. I'm very curious how long I spaced out and said nothing out loud and was only thinking to myself. Very curious. We want the partial derivative of sigmoid with respect to w times x, which is a constant here. And this is the partial derivative of sigmoid with respect to b. Times 1. I think this is how you would write it. And these are the things that we would perform gradient descent on. Ah, that's too loose. I think I'm ready for the question though. Is like, this y is also just z, and it's just a continuous chain. I should probably go further. But at least when I have the question, I can say it. How do I say? This is the notation that makes sense to me. So when I have Claude build it for me, I'm going to have it translated into this medium. So how would I do this? Do we think it can handle? Why not do multiple images? It's not the end of the world. I can take literal screenshots. Okay, so I have the snipping tool for my keyboard, and we're going to do this. And I was looking forward to doing this a bit ago. Let's see. Exit full. Ball chat. Guys, don't break anything. Am I being hacked? Guys, am I being hacked? Okay. YT. Okay. There we go. That's our first image. And then, let's see. This is our second one. That's all it needs. Let's do full screen. And then let's do snipping tool. Let's see. We are desperately relying on, how do I say, Claude, etc., Gemini, technically, AI models' ability to understand what I've written here. And, oh no. I don't think we've had that. I haven't had a fall like that since I started. Since the first few days of making these videos. Oops. Okay, my phone has enough charge. Let's fix the monitor. Okay. What's up? Okay. So let's first ask, does it understand everything I'm looking at? Hi, David. I have this file open. Are you able to process the content of all of the images inside of this note?
Yes, I can process the content of the images. I see two pasted image files referenced in this note. What would you like to know or analyze about them?
So these are my notes, and I'm trying to sort of understand backpropagation for large language models, but I'm first doing it for a standard neural network. And then even before a standard neural network, I did like logistic regression with a single sigmoid activation of a weight matrix W multiplied by a vector X with a bias vector B. Um, and so like the first, one of the photos is just me doing the math on the derivative of the sigmoid function. And then in the upper right of, or the upper left of the second image, you can see me trying to apply the chain rule to my matrix or linear algebra notation form of the problem. And all this is a bit foggy for me. And I'm hoping that you can help me clear up what's going on. First, I care about the how do I say, the basic logistic regression, and then we can stack that to a normal neural network, and then eventually you can help me understand backpropagation for a large language model. Is that something you can do? Can you follow along the notation that I used? Does it make sense?
Yes, I can absolutely do that. Your notation makes complete sense. In the first image, you show that the derivative of the sigmoid function with respect to its input is the sigmoid times 1 minus the sigmoid. In the second image, you are applying the chain rule to find the gradient of the loss with respect to the weight matrix and the bias vector. We can start right there with the logistic regression case. Make sure the matrix dimensions and
Actually,
the calculus.
I have a quick question. This is both a question for me and a way for me to assess your level of detail for my images. I believe that the math in the first image, there's a sub image inside of the first image of an image from the internet doing the math for the sigmoid. And then in contrast, there's my drawing in the blue. In my drawing, I have a -1 that I'm not able to find in the online image. So, as far as I'm concerned, the steps of the math disagree, even though they draw the same conclusion. So, I'm curious if you're able to see which one has the flaw.
I see the difference you are pointing out. In your blue handwritten notes, you rewrite the sigmoid function as 1 plus e to the negative x, all raised to the power of -1, and then you apply the power rule. This brings down a factor of -1, which you then multiply by the derivative of the inside function, which itself has a negative sign from the negative x in the exponent. Those two negative signs cancel out to give you a positive result. In contrast, the printed image from the internet uses the quotient rule instead of the power rule. The quotient rule naturally handles the division without needing to write the expression with a -1 exponent, so you do not see that explicit -1 coefficient in their steps. Both methods are mathematically correct and arrive at the exact same derivative. They just use different
Well,
calculus
okay.
rules to get.
However, an important distinction is I use that negative sign. If you look at the last step for my math and the last step for the image, is they have a 1 over 1 plus e to the minus x times negative e to the minus x over 1 plus e to the minus x. But I have a positive 1 for that second value. I don't understand how they're able to get 1 minus sigmoid from that -1. If you notice that distinct contrast, mine is positive and the images is negative. So which one is the true answer?
The true answer is that the second term must be positive, which matches your blue handwritten math. The printed image actually has a subtle typo in its final step. In that printed image, they write the derivative as 1 over 1 plus e to the negative x, multiplied by negative e to the negative x over 1 plus e to the negative x. That negative sign in their numerator is incorrect because the derivative of the denominator, which is negative e to the negative x, is already subtracted in the quotient rule formula or canceled out by the power rule. Because of that extra negative sign, Their written product would technically evaluate to negative sigmoid times 1 minus sigmoid, which is incorrect. Your handwritten math correctly keeps that term positive, leading to the true
Okay,
derivative of
thank you. I appreciate that so much. So maybe my tangent wasn't useless, you know. Maybe maybe I'm a dog. But let's go back to the standard logistic regression. If you seem to understand the details of the images pretty well. So, um, I think because of how detailed this math is, I think it helps if you were to write it in the markdown file. You have the ability to write LaTeX, so that's completely fine. Um, if you were to sort of like walk me through baby steps wise, you know, first let's just start with only the logistic regression one. Like use my example and my notation and help me understand what's going on, and then we can slowly build up to the normal neural network and then to the large language model.
I have written out the complete step-by-step derivation for the logistic regression case in a new file called backprop It breaks down the forward pass, the loss function, and then uses the chain rule to show how the prediction error, a minus y, naturally falls out as the gradient with respect to the pre-activation value z. From there, it shows how we get the final gradients for the bias and the weight matrix, matching your exact dimensions. Take a look at that file and let me know if the transition from the loss derivative to the parameter gradients makes sense, or if we should dive deeper into any of those steps before we stack it into a multi-layer neural network.
Okay, so I'm going to revisit that conversation because yeah, it's jumping straight to cross entropy loss. I did say logistic regression, so like that's what it should be, I guess. But that's like a messier loss function, um, for which taking the derivative of is like complicating things for us. Um, I think. Um, but yeah, so like maybe we read this and this helps us out. Um, yeah, this is what we came here for. Is we spent an hour. This could be a really long video. Is we spent an hour like priming myself for the context to ask the question. Now we're asking the actual question, and technically I can make it a part two. I'm starting to think about that. That might actually be a good idea. So I might finish here with this as the part two, or as the part one, and then part two tomorrow. We'll go into the neural network and then the large language model. I actually think that might be what's the word? There's like a British slang for it. I don't know. Let's see. Okay, so the forward pass. Yep, yep. You have an X vector, weight matrix W. Wait, what? Oh, we're doing scalar. Yeah, we have a scalar bias. Okay, maybe that makes things easier. Let's do view. So I stop editing things. Okay, perfect. The linear combination is Z, but like, okay, we're calling it whatever. It's a one-dimensional matrix. Since W is one by the product is a scalar, so adding it gives us a scalar Z. Perfect. Then we apply the sigmoid activation product to get our prediction Y, or A, also a scalar, and A will range from 0 to 1. For binary classification, we use binary cross entropy loss L. For a single training example with true label Y, where Y is 0, 1. Cool. Backward pass, deriving with gradients. To update weights and bias B using gradient descent, we need to follow how the loss with respect to them, or we need to changes with respect to them. Yeah, okay. By the chain rule, we can break down step by step how the loss changes with respect to the prediction, how the loss changes prediction with the linear activation, and then how the linear activation changes with respect to the weights and the bias. Yes. So first one is L with respect to A. And I think I'm already confused. Because how do we have a vector? It's a scalar. It should absolutely be a scalar. Oh, we're just using brackets instead of parentheses because it fits better. L with respect to A is, again, these brackets are completely, oh, it's because it's negative. Oh, yes. It's like, how do I say? We want to make it a loss. We want to minimize it. So Yeah. Um, I think it's we're not. Yeah. Oh, entropy is information. So by we're maximizing entropy. It's max entropy, min negative entropy. Maybe. I feel like it's maximum entropy because entropy is information. You don't ever minimize You don't minimize entropy. I think. Um. So we have y, ln a. So that it's just one over. Perfect. Yeah, I think we can ignore the sign for now actually, and then just do this is irrelevant, and then 1 over 1 minus a. Perfect. And then we have the negative there. Take out the negative. Multiply by 1 minus a. Oh, and multiply by a, and then a 1 minus a. Yeah, I'll trust the math for that. That's fine. And then a with respect to z, because we have the definition of sigmoid. Let's see. A equals sigmoid of z. That's literally what a is. A is literally sigmoid of z. Okay. So sigmoid of z with respect to z is given. And then again, because sigmoid of z is a. Perfect. Combine them using the chain rule. You multiply them, and now we have L with respect to Z. Perfect. And then we need to keep going. Is gradients with respect to come on. Sorry, you're not able to see everything. Okay. Um yeah, L with respect to D. We did that, right? Yeah, that's just the multiplication. I'm perfectly fine with that. With respect to the parameters, Z with respect to B is 1. Z with respect to W, this is new. This is new. Z with respect to W. And that is the matrix calculus from the video that you guys never saw. And I'm not used to that. So where's the function for Z? Z with respect to W is X transpose. Yeah. Z with respect to W is X transpose. Yeah. So again, an important topic is matrix calculus. Yeah, I still have the search. And the Wikipedia page. Did I mention at the start? Notation. Let's see. You know what I should do? I should watch a video. Ooh, discussing the paper. Discussing the paper. Whoa. No, there's gotta be a dummy way. What's up with all those transposes? That might be a good watch. Um, doing calculus with a matrix. Yeah, I think that's something that's part of my homework. Is I need to watch one of these videos. Maybe I'll watch it on the train. But yeah, there's just matrix calculus notation is like I can't, not every learning objective cleanly fits into vault chat and whiteboarding. Some stuff I don't know, I have to like consume and come back. Um, yep, yep. And then we just end up with the two thing, and then those are all the things that we update. Is well, how much do we change the bias? Step in the gradient direction. How much do we change the weights? Step in the weights direction. Um, Easily can get very complicated and confused about like the space that we're in and like how we're navigating it and like how like bias and weights are like separate, but like they're just the parameters that we have control over. And again, removing them in a descent direction, and then the fact that we ever reach in a minimizer and that there's any like convexity beyond me, man. Oh my goodness. Yeah, having that, like, I don't know, insurance over like what the surface is that you're navigating, that's a lot. That's a lot to go off of. Um okay, wait. Yeah. Okay, that's it. That's my brush up on backpropagation, like very basic backpropagation. Um and then what's it called? For a neural network, very, very, very close. Again, it's just like, I don't know. I haven't been thinking in like vector spaces like that. So bring that back, and then finally, because I don't think I could just dive into the large language model one, being frank. So this is a good criticism of top down, is like, yeah, is like fundamentals are like fundamentals, like, you know what I mean? I can't some things you can't even talk about on a high level, you know? Um and again, when I say I care about details, the details are at the bottom. That's where details come from. So, full screen. Um yeah, I had fun. I think that was a good video. That was a good exercise for me. Um, hopefully Gemini didn't lie to me about my work being right. Hopefully that wasn't like sycophancy. Um, and yeah, I'll be back for part two, hopefully tomorrow, and I'll watch the video on the train on the matrix notation. This may end up being a three-part thing. I hope not. Hopefully next video I can do like first 30 minutes as we go straight to the neural network, and then the last 30 minutes I go straight to large language model. But this might require three parts because like I'm just completely absent from it. And I do care about this. Why am I saying that? I'm questioning, you know, the correlation of this to me reproducing coconut, and I'm like, um, I care about how many, like, the depths to which the things I'm doing from scratch, you know, and just using PyTorch dot back. Nah, I don't like that. Um, yeah, I don't like that whatsoever. Um, because it's, yeah, I'm not writing kernels for GPUs. Like, I should understand the auto grad graph that we're using to actually do gradient descent. Like, literally, like the optimize your most important thing for your search algorithm. Yeah, so we're not skipping out on that. Even though even though it's gonna take longer to get things done. I think this is a necessary thing for me to lock in on. So see you tomorrow.